Hey folks, how y'all doing? We are reviewing for exam that is on Thursday and Friday of next week. I'll try to get through about half or so of the practice exam today, and then get through the other half on Monday. Um, let's get started. So, in terms of block modes, what is ECB mode considered weak, and what additional step addresses that weakness? Um, and so, ECB mode, we start with a plain text, divide it into blocks, and then we encrypt each block. And then come out with a ciphertext. So on and so forth. And then we encrypt this block, and then we encrypt this block, and so on and so forth. Um, the weakness is if we have blocks that are repetitive, which doesn't often happen in text, but can happen in data files or audio files or image files. We did an example the day we talked about these block modes where we had multiple blocks that were all the same color. We had a large bit of white in our image, and all of these blocks that were the same color encoded as the same color. And so what we ended up getting was just a color swapped version of our image, um, for the most part, and the image was still entirely recognizable for what the original was. Um, so the weakness um, is multiple plain text blocks with the same data, all encode the same way. And so a step that addresses that weakness, this is called CBC mode, um, text ciphertext, is we have multiple blocks here. We'll encrypt the first block, and we get a block of ciphertext. And then we take that block and this block too and XOR them together and then encrypt to get the second block of ciphertext. And that way, if these two blocks are the same, these two blocks will be different because this was just the encoding of the original block, and this was the encoding of block 2 XOR with the ciphertext of block 1. Um, well, then, if we just keep chaining that together, um, take block 2 and block 3 and XOR them together, then encrypt. Then, even if all three blocks were identical, all three blocks of the ciphertext will be different because block 1 and block 2 are different because block 1 didn't have something XORed and block 2 did. But then block 3 will be different because what we XORed in block 2 is block 1, and what we XORed in round 3 is block 2. Both of those are different. So, uh, anyway, this defeats the repetitive issue that shows up in ECB mode. It's one extra step, but it provides a greater deal of security. Okay. All right, moving on. What's a hash function? So a hash function takes as an input a possible set of messages, as an output it produces a set of digests. Um, that's fundamentally what happens, so that the we can verify that the message has been not altered, because if the message had been altered, then it would no longer match up with this digest. Um, so that's the fundamental requirement. Um, because we want the digest to be short and easily transmittable compared to the size of the message, this will not be one-to-one function. But we do want the function to be sort of in a way that's functionally one-to-one. We do not want to have collisions happen very easily. And so our goals for the hash function is that this should be fast, because many systems will need to create hashes for lots and lots and lots of messages over the course of a day. We want this to be what's called pre-image resistant. Which means if I know what the digest is, but not the message, so if the digest has been compromised, that I don't want to then be able to create a second message that produces the same digest, because then so I don't want to be able to reverse engineer this digest into a different message, so that even if I didn't know what the original message was, that this would create a collision, and that's what we would like to avoid. So I can't reverse engineer this digest into a second message. Okay. The second message is likely to exist because this is not a one-to-one function, but there should not be an easy process to be able to identify that message. And the other thing that we want is collision resistance. This way, even if I don't know what the digest is I know what the message is. I don't want to be able to somehow engineer this message into a that allows me to create a collision. So, in one of them, I don't want to use the properties of the digest to create a collision. And in another one, I don't want to use the properties of the original message to create a collision. Okay. All right. So, what does pre-image resistant and strongly collision free mean? So this means that we can't use the digest to create a second message which collides. And strongly collision free is that we can't use the original message to create a second message. Okay. So no part of the algorithm gives me something I can leverage to create a collision. If I create a collision, I have to be able to just reverse the algorithm itself. Okay. The random oracle is an idealized hash function. Describe it. The random oracle is idealized. It answers questions instantaneously. Um, it answers questions randomly if they are new. New messages, but it logs the random answers it's given. But all answers are logged. And it gives the logged answer to a previously asked message. Okay, so how is that um, how does that satisfy the things that we want for a hash function? Well, obviously it's fast because as long as we're being hypothetical, instantaneous is as fast as we can get. And so um, we're hypothetically deciding this. The um, randomness is what helps defeat with the collision aspects. Is that if the algorithm really truly returned a random message, then um, the chance of creating a collision is just one over the possible number of messages, and if the possible number of digests, and if that number is um, well, if the number of digests is large, so one over the number of digests is very small, then I would just have to randomly generate a bunch of messages hoping that I created a collision. I couldn't create a collision by hearing the process because the process was random. Um, but it does have to be a function, which means when I ask the same input again, I can't get two different outputs. And so it has to give me the logged answer if I've asked a question before. Okay. All right. So let's talk about the choice, parity, and majority functions. Um, so we have three variables, E, Q, and R. So their possible combinations are all true, false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, false, false, false. All right. So for choice, what we're asking is, do we choose which function do we choose here? And so if p is true, then we're gonna go and choose q, and so we get true, true, and false, false. If p is false, then we choose r instead, and we get true, false, true, false. True would often be 1, and false would often be 0, by the way. Um, and just using trues and false here. Parity just records how many of these are true, if it's an odd number or even number. So three trues is the same as one true. Two trues is the same as no trues. So those would be false. One true is true. Two trues is false. One true is true. Is true. No trues is false. And then majority does exactly what you expect. Just reports whether the majority are true or false. So those all have a majority of true. This one has a majority of false. True, have a majority of false. Okay. Um, if I had, say, four variables, um, E and Q were true, R and S were false, and I want to know what um, choice of QS or with parity QRS XOR with majority EQR. I should be able to do that because I know how each of these functions work. Okay. All right. So that's number 5. How did SHA-2 achieve greater security in fewer rounds than SHA-1? By changing the round constant every round instead of every 20 rounds. Um, by updating the round constant each round, we have a better defense against like time shifted attacks, and um, that way we didn't need as many rounds to achieve the same level of security. I'm not going to ask you to memorize either of the SHA-1 or SHA-2 algorithms. You should know how choice, parity, and majority work. But the details of going through all of the different steps in each round, just remember, involve rotating by weird amounts and shifting by weird amounts, and then going through some, convoluted permutations. Do not have to worry about knowing what those algorithms. Um, you should sort of know sort of the general history that SHA-1 has been broken, SHA-2 has not. Um, SHA-2, you can either go fewer rounds, which is faster, um, or you can go the same number of rounds but encode a much larger file because you're doing a larger encode. So, all right, number 8, modular exponentiation. Um, given values for a, b, and n, compute a raised to the b power mod n using the halving and squaring algorithm. Um, so, for example, if I wanted to do 3 raised to the 102 mod 7, for example, this shouldn't be too bad. We start with 102 and divide it by 2, dropping the remainder if there is a remainder. And we get these values here. Then we start with the base. So this is the exponent. We start with the base, and we square it each time. 3 squared is 9, but 9 mod 7 is 2. Well, then we square 2 and we get 4. 4 squared is 16, but 16 mod 7, 2. So we get 2 again. 2 squared is 4. But 4 squared is 16. And once again, 16 mod 7 is 2. And then 2 squared is 4. So we started with a 3, but we ended up with this pattern of 2s and 4s. Then we take every odd number in this list and we multiply the even numbers that are next to them. So 2 times 4 times 2 times 4 is 64. 64 mod 7 turns out to be 1. And so 3 raised to the 102 power mod 7 is equivalent to 1. Okay? So that's how the algorithm works. We divide by 2, dropping the remainder each time. We line up the rows that had an odd value for the exponent. We multiply those spaces together, take the answer, mod whatever the modulus is we're doing here, and that gives us an answer. All right, let's keep going. Why is modular exponentiation suitable for public key algorithms? Modular exponentiation is O of log n, but the reverse operation undoing modular exponentiation is called the discrete log problem. Is a trickier problem. It's O2 to the n. And so far, even though we know a couple of special cases where the discrete log problem can be solved quickly, um, like for a couple of certain small primes, in general, this problem has not been broken. It's still in O2 to the n. And so if we choose an n appropriately, we can have the speed of the modular exponentiation be fast, while the speed of being able to break it would be very, very, very slow. Um, and so we just have to choose good values of n. Okay. What is a primitive root? Given two positive integers a and n, determine whether a is a primitive root mod n. So a is a primitive root mod n if let's see, a is a primitive root mod n if the set a to the first mod n, a squared mod n, up through a to the n minus 1 mod n are all different. Okay. If they're all different, then we say that a is a primitive root. And so, for example, is 2 a primitive root? Of 11. So we could try this out. 2 to the first is 2. Squared is 4. 2 cubed is 8. 2 to the fourth is 16, but that's congruent to 5. All right. So then 2 to the fifth would be 5 times 2 would be 10. And then 2 to the sixth would be congruent to 20. But 20 mod 11 is 9. We don't have any repeats so far. 7th would be 18, which mod 11 would be 7. Still don't have any repeats yet. 2 to the 8th would be 7 times 2 would be 14. 2 to the 9th would be 28. And mod 11, that's 6. And then 2 to the 10th would be 12. And it turns out that all of these values were different. And therefore, the answer to this question is yes, it is. Okay. All right. We're going to stop at this point. We're a little over halfway through the practice exam. We pick this up again on Monday. Y'all have a fantastic weekend. Take care.